All right, like usual, good noon, guys. We start in noon. There's no good noon, but we make it. Halas. So today, inshallah, we cover the last segment of this course. And basically, we're going to talk about the bipolar junction transistors. There are other type of transistors, different technology. We'll try to cover some aspects of this technology, okay? Of course, as usual, these slides are not meant to replace the textbook. And they are changed without notice. You can set the notices in the blackboard, but I will do that without setting any. Alright, so as we did with MOSFET, we're going to start with the physical. With the physical view of the BJT transistor and how it works basically. Of course, as usual, we have to see how the voltage between two terminals of the transistor controls the current flow that goes through the third terminal. Same thing that happens with the MOSFET, yes or no? That's it. And of course, we're going to talk about the equations that describe this behavior. And of course, it will have some regions. The same thing with the MOSFET. A lot of similarity between the two. And then finally, we'll try to analyze and design circuits using bipolar, basically amplifiers. Okay. And whatnot. Okay. Then we move on. Okay. Alright, so the new transistor we are going to cover today, inshallah, is the bipolar junction or BJT transistor. It was invented before the MOSFET in the late 40s, in 1948, in Bell Labs, prestigious Bell Labs at that time. So, and they have actually started the new era of industry and academia, which is solid state circuits or solid state technology that includes MOSFETs and etc. 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 Okay, so it's I think it's easy. We can say that this is at least a trillion dollar market. It has huge applications. So we are not going to cover it in here. It was replaced later on in major applications by the MOSFET for reasons we're gonna talk about them later on. So the predominant MOS or transistor technology that we have nowadays is MOSFET, but still we use BJT in some niche markets or niche applications. Okay. All right. So let's go. All right. This is the view. It's not the exact physical view. We'll get to that in a second. Typically, the MOSFET or BJT transistor is composed of three regions. N region. When we say the region now, it means doped. Okay, when we say N-type, we know what it means, or N region what it means. So we have two N-doped regions of semiconductors sandwiching a P-type semiconductor in between. Okay, so it could be N separated by P, we call it NPN transistor, or it could be the other way, you know, as we did like in the MOSFET, changing P with N and see what's going on. And in that case, we get a PNP. All right. So it's like the symmetrical view or symmetrical impersonation, if you will, of the MOSFET. Okay. So it's a PNP transistors. Okay. So that's it. So this is what it is. We call basically, as you can see here, the difference between the BJT transistor and the MOSFET transistor in the physical view. Physical view, يعني الملموس. How does it look like? Okay, this is not symmetrical. This is just, you know, a sketch of the device. When you see the physical next, you will see that it's not symmetrical. It's not. This region is not symmetrical to this region. Okay, this is a very big difference. Okay, so remember that. Take it. So, anyways, so we have one region, like if we take NPN transistor, one is called the emitter, the other end is going to be called, of course, the collector, and the one in between, we call it the base. So these are the three terminals of the BJT transistor. And the same thing in the other one, so we have an emitter and collector, and in between the base. That's it. Alright, and of course, when we have two different doping regions, definitely we'll have what? A depletion region. A depletion region, or what we call it, this device when we have two doped regions. What do we call it? What? No, we have one region semiconductor with another region. So one is N and the other one is P. or P is on the other side. We call it junction or diode. That's it. So these two words, junction or diode, they mean the same thing. But the junction means specifically the region of meeting. But the diode talks about the whole thing. The region of the meeting, including the contact. Okay? So basically we have two diodes in here. We have this diode and this diode. We call this diode the emitter base diode, and this one the collector base diode. The same you see here, the collector base junction or diode, CBG, collector base junction, and this one is emitter base junction. Okay, the same thing in here. Okay, the emitter base junction, and this one is the collector base junction. This is where the junction is. Okay. So this we are just describing. So the first thing on anything we describe. Try to understand how does it look like and the definitions. So these naming are not for fun, because later on when we study it, we are not going to revisit what it is. We know that it is. Okay? When we talk about that, خلاص, we know what it is. So when we talk EBG, we mean what we know. Okay? Move on. Okay. All right. So we are going to talk here about the modes of operation, but in a very high level. Means we don't go in details in here, but okay. So as we said, we are having here two PN junctions, okay, like for PNP or NPN, okay. So we have always one junction, or two junctions, this one and this one, and it is between PN, okay. So we are the first one. We have, as I mentioned to you, the emitter base junction, okay, PN, okay, and we have the collector base junction because PN, okay. Yeah. So that's it. So we already spoke about that. So this is the new in this slide is that the operating modes, I mean where this transistor works or how it works. We have again here like three regions again. We have the active mode, we have the cutoff, and we have the saturation. Okay? The active mode is used actually for amplification. So this is the one that we need to pay attention to. And the others, they are also important, the cutoff and saturation. They are also important, but only for switching. Switching means when we talk about switching, we are talking about? DC. Not DC. No. But a switch, what's the application of switch? Is it amplification?
No.
I mean, how to switch? It's on or off.
Yeah, what's that? What do we call that? Digital. Digital.
Professor?
Yes.
Do you have a triad region here, like in the...
We'll come to that. Thank you for the question. We'll come to that right now. Do you got that? People, they forget that we are dealing with either digital signal or analog signal. So when we talk about amplification, we're talking about analog, yes or no? But when we talk about switching on and off, we're talking about digital. Agree? We need to agree all the time. If there's any question, please do not hesitate, okay? Alright, Bilal, clear? Alright, so please put that in mind. Digital, analog, always in your mind, okay? Alright, these are the conditions, okay? Always, for any region, we have conditions. Yes or no? We have conditions in MOSFET. Now we have conditions for the BJT. Here are simpler a little bit. Okay. So for the cutoff mode, okay, the condition to have a cutoff mode, the emitter base junction need to be reverse biased. And the collector base junction need to be also reverse biased. So when both junctions are reverse biased, we have a cutoff. Both they have to be. I said here, see here? Plus, they have to. Or if you want, and like this. Who knows this? I like this. It's a nice one. Okay, so this column is this and that. Okay? Good? Very good. Now for the active, the condition for the active mode is that the emitter base junction need to be forward biased and the collector base junction need to be reverse biased. Okay? And the last not least, the saturation need to be, the opposite to this, forward, and the collector base need to be forward biased. Now, Mohammed asked a very good question, triode and saturation. Here in BJT, which is very excellent question, here in MOSFET saturation is for amplification, yes or no?
Yes.
Correct? But here saturation is for switching. We don't have triode here. Do you understand? So if you want to make similarities, cutoff is cutoff, means there's no current going through. That's it. So it's the same thing. Saturation of the MOSFET correspond, if you want, the saturation of the MOSFET correspond to the active in here. Because for amplification, here active, the other one we call saturation. Correct? Did you get that? Did you get that? Here we call it active region, that's where the amplification. In MOSFET, saturation. You understand?
Yes.
Alright, good. So for the last region would be here the saturation and there the triode. They are not exactly the same, but they are equivalent. You understand? So cutoff, saturation active, and triode saturation. You get messed up a little bit, but you get used to it. So the saturation of the BJT is not the saturation of the MOSFET. This is what you need to take from here. Do you understand? And here we don't have a triode. Good. And feel free to ask, huh? Do not stop. Okay, good. Alright, so the active mode, of course, is the most important because we need mainly this course. We are especially interested in amplifiers. It's the most important. So in this, what do we have? So what's the condition for the active? I know we just studied it. We did not even, engrave it in the mind. What's the condition for the active? Reverse? No, Muhammad?
Forward.
Who was forward?
EBG.
Yeah, okay. Emitter base is forward, and the collector base reverse. Okay.
What the first one was?
Reverse.
Cutoff.
Yeah, I told you, I don't blame. We just studied, so we took time for.
Yes, the collector is forward and the.
No. When we say the forward, we're talking about two.
No, if
collector base.
And the other is reverse.
Okay. Here, very good question too. We are talking about the current that goes from the emitter to the collector. Do you understand? Not from the collector to the emitter. That's a good question. Do you understand? So, in this circuit, for example, the current is supposed to be. Sorry. Here, there's two things here. We are talking about electrons or the current. Okay. So the current actually goes here technically from the collector to the emitter. But here it's called emitter, so it should be from the emitter to the collector. Yes or no? Collector means مجمع. صح ولا لا? Understand? But here, when we say emitter and collector, we are talking about electrons. So actually, the emitter emits the electron, send the electrons. That means the current is coming to it.
Yes.
Do you understand? And the collector is the collector of electrons. That means the electrons comes. That means the current is going out of it. Do you understand? So that's also an important, thanks for asking, an important observation. Okay. So we said that here, first of all, pay attention to something really important, that here, most of the time, here, as we did with MOSFET, we're talking about NMOS. Here, most of the time, we're going to talk about NPN. This is number one. Do you understand? NPN, BJT. So NPN, BJT somehow looks the same like NMOS. Do you understand? I'll tell you why. Because for NPN, the carrier that goes is actually electrons, the same like NMOS, yes or no? For PMOS, the same like PNP. Because the carriers that move, or the major carriers, are actually the holes. And of course, which one is faster, the electron or the hole? The electron. So that's why NMOS is the most popular transistor, yes or no? The same thing for here. The NPN is the most popular BJT because the electrons are faster, okay? Got it? Khalas? Very good. So of course, to bias the transistor, we need two power supplies. You see, this power supply makes this reverse or forward? This.
forward.
hold on. Who raised your hand? You. الكعب. يلا. محمد.
Forward.
This makes forward. Why?
Because the negative is connected to the end.
That's right. Very good. Yeah. Still the memories of the diode still works now. I thought that March break has broken all the memory. Seems we have something here. That's good. That means you have a hard disk here. That's good. Instead of RAM, because RAM is volatile, yes or no? If we take the power off, bye-bye. So the memory that was lost during the March break, all was RAM. But the others are in the hard disk, yes or no? Just to throw some jokes here. Alright, good. So, yes, so this guy is, so the emitter base is forward biased, as you can see, negative to the N, positive to the P, bingo. And this one is reverse because the N is connected to a positive and the P is connected to the negative. Bingo. That's it. Alright, good. So, as we do that, so basically we are injecting the electrons from the emitter to where? So when the electrons come here, let's see, maybe it's actually explained later on. That's why. Let's put it for now like this and we'll come to it next. Okay? Alright, let's see. Okay. I will explain this where? In the one previous. So when this is forward bias, okay, so the electrons can move freely from this to there, yes or no? So the depletion region here is what? Wide or small?
Small.
Small, yeah, because it's forward bias, yes or no? So let's just make it just a little bit like that, okay? But this one, the depletion region is what? Wide or?
Wide.
Small. Wide, very good, very good. So it's a little bit wide. Why? Because this junction is reverse bias, very good. So what happens exactly? So the electron gets injected from here to the base, and as soon as they arrive to the base, they find holes, yes or no? So some of them will be recombined, okay? And because they get recombined, the number of holes will also decrease. So that number of holes will be compensated by an electron, by the positive charge from the battery to keep the equilibrium. Oh, we got lost, we need something, so this guy is support, okay? Very good. But then, the electrons, as soon as they arrive here, they will see a huge depletion region here. So let's say here, let's see, the electrons, they are like what? What color we can give? Let's say blue, okay? When the electron gets here, sorry, oh, see. All right, let's see. Green gets there. So let's say the green again. Okay, bye. Okay. Now let's say this electron gets here to this depletion. Where does it go, in your opinion? You want to answer? It's just fine. Make mistake. That's fine. Just tell me why it goes that way. Yeah, you are right actually. But why? Anybody? Why the electron will have to be swept? Why?
The positive side.
Yes, Muhammad?
The positive side of the battery.
What's that?
The positive side of the battery.
No. Listen. Let me make it very clear. When something moves, we will talk about a force. صح ولا لا? Newtonian, yes or no? We believe in Newton. So what's the force that pushes actually the electron to this way? It's true. No. Yes,
The density of electrons in the collector are much less than the...
No.
The electrical field?
Very good. Explain that to us. That's fine. No, hold on a second. What is the electric field? Yeah, it makes sense. صح ولا لا؟ لأنه charge gets moved by the electric field. يعني actually the electric force. صح ولا لا؟ So explain to us.
The electron will be directed in the reverse direction of the electric field.
Where is the electric field going here?
From positive to negative.
From here to here. Is that what you mean?
Yeah.
So this is the electric field. How did you find that this is the electric field?
From the positive to the negative.
Because of this. Yes, because this is the pole here. You see, this is positive. So therefore, the electric field from here, because this is high, so the electric field is going like this.
So the electrons will move.
Not only that, but also actually is the total electric field, because there is electric field due to the unbound charges. Yes or no?
Yeah.
The depletion region, صح ولا لا? Which is V naught actually. We call it E naught. Now that E naught gets strengthened by the electric field of the battery, so it becomes bigger. That's why it's wider. Make sense? So the electric field going this way, go Ali.
The electrons will be directed.
Why?
Because it's opposite polarity.
Because F is equal to Q in this case is minus times electric field. صح ولا لا? So it's gonna be opposite. Very good. So it will go then this way. Bingo. خلاص. How is the how? Very. So when we explain these things, when we explain physical phenomenon, we have to use physical what laws. You understand? That's the way to explain. Okay. Move on. So that's what's happening in the active mode. That's all what we need. خلاص? Very good. So what we said is explained in here. I'm not gonna, repeat. Okay. So the emitter current is the current of the emitter. It means it's actually coming to the emitter, not out. Because the emitter emits electrons. صح ولا لا? So that means the emitter current come into the emitter terminal. صح ولا لا? Explain that. Very good. Is the current that flows across the emitter base junction. It flows out of the emitter lead O. Here, then in this case, we mean actually, here, out of the emitter lead, we mean the electrons here.
Yes.
Do you understand? Electrons. Let's go back. Let's see if that's true or not. So, talking about the emitter current. So, emitter current. This is the emitter current. So the emitter current that goes this way is actually flow out of the emitter is actually of the electrons or the positive charge is actually of the electrons. Yes or no? So that's what is meant in that slide. Do you understand? I'll try to update it in the future. Okay? Do you understand? So the emitter emits the electrons in here. That's what is meant in that slide. Okay? So in that case, what is that? Next, okay. So flows out of the emitter. We mean here in this case for this statement the electron current. Okay. So the minority carrier here in the P region means in the base. Yes or no?
Yes.
That's where it is. Okay. So these electrons will be injected from the emitter into the base. You see, and that's the proof that we are talking about electrons. You see, because it's taking these electrons. Do you understand? These electrons, that means these guys that are moving from the emitter. So it emits the electrons, not a positive charge. Very good. So they will be injected from the emitter into the base. Alright. So because the base is thin, and this is the physical reality, the base is made really, really thin. In the nano range. Means 10 to the power minus 9 meter. Okay? So the concentration of the excess minority, what are the minority in the base? They are the electrons. Okay? Yes or no? Majority are the holes. So because the base is thin, concentration of excess minority carriers within it will exhibit a constant gradient, of course. Okay? So here the minority are the electrons in the base. The majority in the emitter are what? The electrons. So because there is no barrier, of course the diffusion will go, and that's why we call the diode current is actually diffusion, mainly, okay? Do you understand? There's no barrier. If there's no barrier, because the forward bias, or the barrier is very, very small, because it's forward bias, here in this case, we let the diffusion be the phenomenon, yes? Yes or no? Because electrons here are huge, and here are very little. The gradient is high, they move.
Professor?
Yes?
I have a question. Here in the diagram, we said that the collector's part collects from the battery and sends it to the emitter.
No, we are not talking about battery. Can you repeat that again?
Yeah, when we said the collecting part.
Okay, when we said the collector, we said it collects the electrons.
Yeah, the electrons from the...
It collects the electron, and then don't complicate it. It collects the electrons. Yes.
Okay.
From where? From the emitter, because the emitter emits the electron, and the collector will collect them. But there is a little bit of those electrons that will be dying in the base because the base is P. Okay. Yes or no? So not all of them they come along. Some of them they will be, annihilated by recombination. Yes or no? And not all of them will come. Do you understand? So somebody shoots and the other one is collecting. Like somebody is throwing like American football. Somebody throw the ball and the other one get it and run to the goal and then hooray. Got it? So the emitter shoots the electrons exactly like that. And the other guy collect it and go. And that's the point. Okay? Good. Alright, so here basically we are talking a little bit in terms of, graph and equations. So hole here in the emitter, the holes are what? Minority, yes or no? So this is what you see here in this line, okay? This is basically the carrier concentration. So there is a level here, okay? That level, we call it equilibrium. It means before we put any electric field, yes or no? So the holes actually, because here we are forward biasing, so basically the electrons will move this way and the holes will come opposite to them, yes or no? So therefore the holes that comes from the base, they will increase the minority here at the junction, yes or no?
Yes.
And then they will decrease eventually. So makes sense. Here the same thing for the electrons. Here the electrons here are the minority, yes or no? NP. Okay, this is the electron concentration. Okay, electron concentration also will increase at the edge of the boundary. Here, what you have here between these two lines is the depletion region. So, as after the depletion region, the minorities that are high. The minority here of what? Of the electrons, because the electrons they've been sent from the emitter to the base. Yes or no? So they become here minority, and their density will increase. Now, somebody may ask, why this minority here are like this, and the minority here are like that? Does that make sense? Good question. It's because in fabrication, when they fabricate, they make sure that this guy, the emitter, is highly doped than this guy, the base. Highly doped means, if it's highly doped, that means here we have too many electrons as majority than this, too many holes in here. So that's why when these guys move from here to there, they don't increase much in minority here. But these guys, when they move the electrons from the emitter to the base, their influence is huge. You got it? Very good. So that's what it is. And of course, the gradient, the electrons, not all of them, they will pass to the collector. Of course, they will decrease because some of them will, what? Will recombine. Okay. Here is the ideal. Here, ideally, we want them to, recombine in linear fashion. But in life, actually, they are in non-linear fashion. Okay? Of course. So if you make the base width smaller, what happens? We collect most of them. Make sense? If we make it wider, they will die even before reaching the collector. Got it? And this is another reason for BJT. We make the base as thin as we can. Got it? In fact, we make it as thin as to make it fully depleted. It means this depletion region of the collector base, we want it as close as this region. So that most of the electrons that sent by the emitter will be collected by the collector. Got it? We want this decrease to be as small as possible. That's it. So that's what it is. So this is what we want, and then move on. That's it. Okay. Here I want to take it to make it just to refresh your mind. Here we said that the emitter base is what? Forward. Yes or no?
Yes.
That's why we have this. Oh, very good. Forward means what? That the P is bigger than the N. يعني VBE positive or negative? VBE means VB minus VE. صح ولا لا?
Positive.
VBE is positive. Follow me, make sure you understand this. Now, the collector base is going to be reverse bias.
Yes.
The P is less than the N. Yes or no?
Yes.
The P is less than the N.
Yes.
Make sense, Muhammad? Sync or not sync? You look disconnected. Okay, let's repeat. We said that the collector base need to be reverse bias. صح ولا لا? Emitter base has to be forward bias, and now, for that matter, VBE has to be positive. We understand that, yes or no? Because VBE means VB minus VE. صح ولا لا? So VB, which is the positive side, أكبر من ال VN اللي هي هنا emitter side. صح ولا لا? So this is forward bias. Got it? خلاص? Clear? Very good. So this is clear. Now, for the collector base, it needs to be reverse bias. معناته base voltage is less than the collector voltage. صح ولا لا؟ لأنه هذا is P and this guy is N. Remember this? We are talking about NPN. Do you understand? Here, that means this voltage has to be less than this. Because the reverse bias, correct? Yes?
Yes.
It seems I'm speaking alone here. Clear ولا?
Clear.
I can buy you a coffee if you want. Cappuccino or anything. Okay?
That's great.
خلاص clear ولا لا؟ No, it's okay. If it takes time, we can wait.
Yes.
Clear؟ خلاص؟ لأن وجهك بيكون حاجة أخرى. Okay, great. So the P side of the junction has to be less than the N side of the junction. صح ولا لا؟ That means V what? VCB, VCB. That means BC minus VB. Also, we need to be
Positive.
positive. Good. And here is the condition for the active mode. That's that. We are studying so far the active. We're not caring about the saturation and the cutoff. We are looking for the amplifier. صح? Good. Sarajdi. Very excellent. Alright, so the current flow. So our target is to get actually eventually the equations that are governing or controlling the behavior of the BJT. Alright, to do that, like we did with the diode, we have to look at the concentrations, and from there we build the current, and then eventually we get the IV characteristic. Okay. So the concentration of the minority carriers means this NP. What are the minority here? P will end here
N.
when we write
N,
like
N.
this.
N.
So N. They are minority. Where they are minority?
And P.
In the base. صح ولا لا? So boundary the boundary of the emitter base junction. So we are talking about these. And the boundary means just after the depletion. صح ولا لا? Okay, is defined by the previous equation that we studied before. We studied this before. Here, NP0 here means what? Means at the boundary.
At the.
At the boundary. At the boundary of what? The boundary of the emitter base junction. Where is that? Is this one. This one. Okay. Clear?
Yes.
Fine? Good. So let's move on. I want to make sure that we are on the same page. So they are equal of
NP.
the equilibrium concentration, like we studied before. Again, I'm not going to repeat the diode chapter. You need to revise that. Exponential VBE over VT.
Okay.
Clear? VBE is positive, صح ولا لا? VT is positive ولا لا? إيه خلاص. Exponentially will increase the minority. Do you understand? The boundary. We are not talking about later on. Okay. Good. So this concentration now, we said that, so this is now known. Concentration of minority carriers NP at the boundary of the collector base. Very good. Is actually zero. What do we mean by that? We mean by that this. So this minority, they have to decrease, and eventually get to zero. It means the excess, الزيادة excess of the equilibrium. This is the equilibrium concentration. فالزيادة هذه that minority eventually goes to zero if it is wide enough, okay, at the depletion region of the collector. Alright, okay. So the positive VCB actually, the positive voltage between the collector and the base, it actually causes these electrons to be swept across this junction. Okay? We don't want them to die, we want to collect them. So if you make the depletion region wide enough between the collector and the base, it will throw them to the collector. You understand? It will bring them. It will not let them die if we make it wide enough, the depletion region. Or we make the base small enough. Good? So we are saying the same thing, it's just a different wording in here. Alright. So, okay, good. So the tapered minority carrier concentration profile exists. That means that profile, this profile, okay? Tapered magneto is not horizontal or vertical, it's like tapered, it's like may, okay? Okay, منحنى تاع minority carrier. It does exist. It causes the electrons injected into the base from where? From the emitter, okay? To diffuse through the base to the collector. That's what we said. As such, okay, the electron diffusion current IN, it does exist. And what is it equal to? Alright, this is the diffusion current, yes or no? We studied that. Huh? Remember that from the diffusion course? Really, we are going really back, really. Far to the two types of currents, and it was second class, I believe. Or third, okay? Good. Something like that, third or second. Anyways, so this is the equation for that. Alright, great. So that, because we have here the profile, it's not constant, it's tapered, so there's a gradient in here, yes or no? We are talking here, where? In the base, yes or no? صح ولا لا? So that, because we have a gradient of concentration of the minority carrier, so they will create a current that goes like that, and that's it. Alright? That's it, so this is what it is, and basically, that gradient, we will take it where? Here, okay? Because it's not gonna change along. Okay? Alright, so bingo, we continue there. Of course, we said that some electrons will die in the base. We know that. They are combined with holes, which are the major or the majority carriers there in the base. We said that. The base is thin, however, and the combination is minimal. Yeah, we said that we try to make the base as small as, because we need the electrons to move, yes or no? So we make it thin as possible, so that they don't have enough time to die. Okay? That's it. So minimize their combination. The combination still does exist, okay? And that's why the gradient is still curved, okay? Alright, so that's what it is. So here just, just a show of what's going on. Alright, so that's it. So we just explained that. Now, the collector current. So we started from the emitter. We are going to the collector, step by step. Alright, so now, the collector current. Okay, let's first discuss what's going on, and then we'll come to the equations. Alright? Any question?
No.
Question? Okay. If there is any question, stop me, because I'm speaking. I do not know whether you don't understand or not. If you don't stop me, I will not know. Good. So what we observe, of course, that most of the electrons, they will be collected at the collector. This is what we know. Good assumption, not too bad. Okay. Boom, it gets there. Because the collector is more positive than the base, because it's what? It's the collector is more positive than the base. More voltage, we are positive. The collector is more positive in terms of voltage. That's what we mean. It's more positive than the base. Why? Because it's reverse biased. Yes, that's what we mean. That's what we mean. Then these electrons are swept to the collectors. We are saying the same thing. We are repeating basically. Okay, so the collector current, IC, this is the thing. And as you can see here, I is small and C is capital, means we are talking about what? What one? Instantaneous. If there is any AC also, we'll come to it. Yes or no? Okay, good. So is approximately equal to IN. That means the whole, we said that the recombination is made minimal. That means the whole electrons will pass through their, what? To the collector. So in that case, IN that we just found is almost the same as IC. IC means the current at the collector. فهمنا ولا لا؟ Clear, Ali? خلاص? Very good. Yeah, we're talking about instantaneous. Here is I'm just refreshing you, okay? Still, we do not have AC or DC here. Mainly, I mean, so far we are talking about DC. We're not even talking about AC. But it's just to refresh your memory, about the notation, because you are supposed to know the notations. We explained that, yeah? That means if I put that in the exam or quiz, I will not tell you this is the instantaneous. It's for you to know. Clear, everything? Khalas? You understand? We are not going to repeat that. I'm not going to tell you this is what it is. You are supposed to. I put it into between brackets. Okay? So now, then the collector is the same as the, this is what? The same as the IN that we just calculated. Yes or no? IS VP over VT. This is the current from the what you call the emitter base. Bingo. That's it. That's it. So that's what it is. And this is the IS. We studied that. So it's not really something new. And here, actually here, it's an approximation of IS. If you remember, we have something. There's ND and blah blah. Here the approximation says that the acceptors, what the acceptors are. We are talking about the acceptors in which? In the emitter or the base? And the base, why? Exactly, because the acceptors, they generate holes. And because they are in the denominator, the smallest number will win, yes or no? So the biggest one will. That's why I told you that the emitter is highly doped. It means that, because if you remember, I asked, has something over an A, something over an D. Remember the quiz? So 1 over ND is so small that we throw it away. Do you understand? Do you understand? Good? Again, this course is connected. Now we are basically closing the loop. We are closing what? The loop. Because we are at the end of the يوم نطوي السماء كطي السجل للكتاب كما بدأنا أول خلق نعيده. Back to square one. That's it. That's it. Anyway, so this is just to say something that deja vu. We have seen that. So now we are coming to the end. All right. So I see in this case the current of the collector is independent of.
VCB.
That's it. It's dependent only on VBE. Sure. Did we see here? Look at this. Do you see any VCB there?
No.
So the collector current does not depend on the reverse bias. Although it's not the collector, it should depend. But technically speaking, it's not there. It's only dependent on the other junction. It depends on the other junction forward bias, VBE, between the emitter and the base. That's it. It doesn't depend on this one, yes.
But if you have VCB, we mean that from the collector to the base, right? We're not talking about the...
Yeah, collector to the base.
Okay.
That means that voltage does not influence. It needs to be what? It will be, we can just do the reverse bias. That's all what it does. But it does not influence the value of the current at all. Do you understand? Because the current is created on the other junction. This junction, it just collects. Correct? Correct, Bilal?
Okay.
Everybody's with us? Good. Story is very exciting. Okay, so that's it. Bingo. So now we get to the saturation current. That's the one that's in the equation. We said that one is actually particularly important because it's inversely proportional to W. You see that W? So if you make the width very small, IS will be very high. Yes or no? Very important. And of course, it depends on the area because remember, there's a cross section. It does depend on the area. Why? Go back. Just always, when you talk about anything, you have to look at the formula. The area is there, yes or no?
Yes.
It's the area, the cross section between the emitter and the base. So the area we need to make it as big as possible, and the base as small as possible. All right. That's it. Typically, these are the values of this IS, and is also called the scale current. When we have the opportunity, we'll talk about why we call it scale current. Good? Good. All right. Now we are getting to the spicy part. All right, getting the equations in here. So the base current, IB, what is that base current? Remember, we said that the electrons will come from the emitter. Some of them, they will die, and eventually the battery has to supply the dyed holes, because the holes, some of them got killed, if you want, by the electrons. لما عملوا recombination at the base. So some current has to be injected to the base to restore the number of holes there. Very good. And that current, we call it the base current. So we know the origin of the base current. Alright, it's composed of two components or two currents, IB1 and IB2. What's IB1? Is due to the holes injected from the base. Yes or no? Because we said it's forward bias, that means the base injects some holes. Yes or no?
Yes.
So that is number one. Number two is actually due to the holes that have to be supplied by the external circuit. That's what we mean. This one. So it's actually, I didn't put the whole story. So some of them will come from battery, as I mentioned just now, and the other one is actually sent by the base. Okay. So the current that comes from the battery is to supply or replenish, if you want. Replenish معناته إعادة إملاء of the holes that got annihilated in the base by the electrons coming from the emitter, And the other component of the hose is actually the hose not dyed, the hose that has been injected from the base to the emitter, because it's forward bias, remember? You got it? Remember, let me get you a little bit there. Let's see. Let's see this circuit again. So, okay, so sum of it, that's what it means. So this one is actually IB what? 2. Okay. IB1, you can see it here. IB1 is the number, the hose that got from the base to the emitter, because this is forward bias. The electrons on one side direction, the holes on the other direction. Do you understand? So this current plus this current is the total current coming here. So in other words, so this IB is actually not, okay, let's put it in a correct form, okay? This IB is the total IB1 plus IB2, this one. That got is actually the amount of current that got it does created because of the dyed holes. So those dyed holes need to be replaced by IB2, and some of the holes will go also from the base through the emitter. So this current plus this current is going to be the total current there. Okay. All right, good. So let's keep moving now. Yes.
The base current, is it independent of the width?
What's that?
Base current, is it independent?
Yeah, of course, because remember the hose that comes from the base to the emitter, it has to depend on the area. صح ولا لا؟ That's it. Okay. But a little bit complicated because it has two components from here and from there, you know? So that's why. But definitely it will depend on the area. Yeah, there's no question about that. Thanks for asking. Okay, let's move on. Bingo. Did we study this? Okay.
Yes, we did that.
We did, خلاص, yes.
Slide 16.
Right. So let's go.
Yes, here.
So we are here. خلاص, very good. So, bingo. Here, this current that we call IB has a specific equation. That current is actually a fraction of the collector current, which is almost the same as the emitter current. صح ولا لا?
Yes.
So IC is almost, actually, let's start. IC is almost the same as IE. صح ولا لا? But IB is very small. It's actually equal to IC over beta. We'll look at beta next. Here is a technology number. So it means it's constant number. And it's quite big. Okay, it's not equal to 1 or 2. It's actually in the 100 range. That means this IB that gets into the base from the battery is actually a fraction of the collector current, which is same as the collector. Okay.
And it is without unit, yeah?
Which
No unit.
Beta, of course, because this is current. This one must be
No
unit. No unit, absolutely. But again, this is a technology constant. Every BJT has its own beta. We are not going to dig deep into it, but that's what you need to have in mind. Okay? We'll come to beta. We are not done yet. So if we now replace IC with its value, it's going to be IS divided by beta E VB over VT. Understand? Any question? Bingo. That's it. We are getting to So now that gain or beta is just kind of gain, because later on I've told you we'll use it. We'll see it in the amplification. So we call it the emitter, the common emitter current gain. We'll explain the naming later on. Is influenced by two factors. But it is constant. Depends on the fabrication of the BJT. The first factor is the width of the base. Because it's technology, yes or no? Use fabrication, صح ولا لا? Very good. And it depends also on the relative doping of the base emitter region and relative doping of the base emitter region, base to the emitter. Okay? That means NA. Where's NA again? In the
base.
In the base or in the base?
Base.
And ND is in the. So the ratio between the two also influence beta. You understand? The ratio between the two. Excellent. So this is a thing. High value of beta get when we get high value of beta, if we make the base as thin as possible. In the nanometer, as I've told you. And of course, in lightly doped base base, we need to make it as slightly low as possible. And of course, the emitter has to be as high as possible. So when we make this ratio as high as possible. Got it? Clear or la? Because when, this as low as possible. So if we make this as low as possible, and because ND has to be as high as possible, and NA over ND also as low as possible, it makes beta as high as possible. You understand? I repeat. If we make the width of the base and the ratio as low as possible, and the ratio of the acceptor doping of the base compared to the donor concentration of the emitter, to make this ratio as low as possible, we make beta as high as possible. Got it?
Yes.
Class? Very good, let's see. Too much today, yeah? Too much information. I've told you that. You need to keep the revision. Alright. Kirchhoff. Oh, end of. So today, this is the last slide. Where we are actually today? We are almost on time. صح ولا لا? Very good. So this is the end of today's class. Yes or no? So all currents, Mr. Kirchhoff says that all what comes in has to go out. And the same for business, same for dunya. What comes in must go out. And in that case, how many currents what we have here for NPN? We have this current that goes here and here. So how many we have in? Easy. Here when we talk about electrons, we are mixing here things. Hold on a second. We said, okay, let's see. Ooh. Now the pen becomes a razor. Smart board. Alright, good. So let's get back. So let's see. N, P, M. We said the electrons comes in the what? In the meter.
Yeah.
So that means the current will have to. Very good. So this is what? This is IE. And the collector collects the electrons. That means the current not does them. It has to leave. So this is the I what? I. This is IE. This is IC. Very good. And we said that IB, which is of the positive holes. Positive holes. It comes in. So this is I what? IB. So what comes in? This guy. Goes out. This and this. Well, comes in. No, hold on. Comes in. This guy. This comes in.
Yes.
And this also comes in.
Yes.
See?
Equals.
Has to come out. Which is this.
Yes.
Bingo or not bingo? Bingo. Very good. Very good. Because IC is very close to IE. That's what I said just now. Why? Because IB is very, very small. So we can ignore it when we compare two big guys. Do you understand? IB is so small.
Yes.
So that's why we can write it like this. And we can claim that IB is equal to, almost equal to I. IC is equal almost to IC. IE is almost the same as IC.
Small.
So IB is actually, technically, is very, very small. So we can write this equation.
Decrease the width.
Now we say that we did what we need to do.
Yeah.
We made the width very small, and we made NA over N and A over NB very small too, to make beta very high, so IB will go small. So in that case, we can ignore this to these guys. Very good. So the first equation, so here comes the equations. Remember, we said that IB is equal to IC over beta.
Yes.
When we replace IC equal to IB by IC over beta, we get this.
Yes.
Beta over beta is IC,
Yeah.
Yes.
and 1 over beta IC is IB.
Yes. Okay. Yeah.
Clear? Bilal?
Yes.
You are with us or with them? With us, huh? Good. So we can write this, and that's it. So this is what I see. This is I. So in that case, we can write this and this. So here we have this is the factor that relates IE to IC. So if I want to write IC with respect to IE, So I have to take this one with the other side and flip it, and it's give me alpha. Alpha is basically what? Beta over beta plus 1. صح ولا لا?
Yes. So.
It's just the way how to write the equations. That's it. And of course, from this equation, I trust that your math is not bad. Huh?
Yeah, we can find alpha.
We can find alpha بدلالة what?
Beta plus.
Beta بدلالة alpha. Okay? صح ولا لا? Just play around with that equation.
Yeah.
Bingo. And of course, now from this equation, we can get what? IE. So IU is going to be equal IC over alpha. We know IC how it is.
Yes.
Over. Finito. Finish. خلاص? Exciting, huh? Thank you very much and see you inshallah next class.